Thank you for inviting me and also the rest of the guys from Germany to this very interesting workshop and this very nice environment, actually. We have already enjoyed it quite a lot. And my talk is about energetically consistent ocean models, ocean model parametrizations. And I have a list of co-authors here, and I want to start with a schematic showing you different dynamical regimes and dispersion relations of waves on a space-time diagram. Here's space in terms of wave numbers or scales from 1 meter to like the global scale, and also periods from seconds to thousands of years. And you see here the gravity waves in between the frequencies of the Coriolis frequency and the stability frequency n. And we have Rossby waves, which is this blob here, which is much slower apparently. And the solid lines are actually the dispersion relations of the actual Rossby waves. Comes in different flavors or modes. Also the gravity waves. And this line here is the surface waves. And this is all separated here from small-scale turbulence, which I won't talk so much about. But I want to talk about gravity waves and the Rossby waves. And to get some idea about my audience and also to learn each other, maybe we can ask here, who knows about gravity waves in the ocean or the atmosphere already? You can lift your hand or raise your hand if you know about gravity waves in ocean or atmosphere. And who doesn't know about gravity waves? Nobody. And who doesn't know how to know about gravity waves even? Also nobody. Okay. So then few of you are not familiar, and I hope that I can at least bring you some aspects of gravity waves a little bit nearer to you. And here's Rossby waves. Do you know about Rossby waves? Who knows about Rossby waves? I know about Rossby waves. So, and who doesn't? A few, okay. Then I hope that you will also learn something at least about Rossby waves. And also waves in general, maybe. And the other aspect is models. We have ocean models, part of climate models to predict the future climate. That's of course very important. But you all know that computers are, the resources in computers are restricted, so you cannot cover all this domain here. Maybe you want to cover this part because that's the climate, or interesting for climate, the large scales and the long scales, long time scales, right? But then you cut off most of the other stuff here, the gravity wave branch. Small-scale turbulence is not modeled then, or it's not simulated. And that's the reason you need parametrizations in ocean models to get the effect of the processes on the smaller scales in your climate model and to predict then the climate accurately. And this is what I want to talk about, also to get an idea how to construct such a parametrization. So gravity waves. We talk a lot about internal gravity waves in the ocean and the atmosphere, but of course there are also surface gravity waves, which is the dispersion relation here. You see it's a bit different from the rest of the internal gravity waves. And they are at the air-sea interface, right? You can see them if you go with a ship on the sea or on a lake or a river. You always see surface gravity waves. They also come in different flavors, short, long waves, but that's not the point here. The point is that they propagate horizontally along the surface. You can also have in the ocean or in the atmosphere 2 layers of different densities. Then you also have a density jump between the air and the sea. You have here 2 different fluids, and then you can also have an interfacial wave propagating horizontally along this interface here. But what we mean with internal gravity waves is because in the ocean and atmosphere we have continuous stratification, so not 2 layers, but continuous change in density. We have internal gravity waves, and they also propagate vertically. That makes them special, and that's a key aspect of them, the vertical propagation and the characteristics of that. They are a little bit difficult to see in the ocean, the internal gravity waves. In the atmosphere, you can sometimes see them here in this picture, quite distant from India maybe, but maybe you also see this sometimes in India, this structure of waves, this wavy structure. You can see in the part of the wave cycle is producing clouds and the other one not. And you see here these wave trains in the atmosphere sometimes. As I said, in the ocean, it's difficult to visualize, but we can measure gravity waves. And here are some iconic measurements from this paper in terms of a frequency diagram of velocities at a mooring in the ocean and a vertical wave number spectrum from drop zones from a ship. And what you see is the spectral energy density. And in the frequency, you see the Coriolis parameter always peaks up as a peak here. And then maybe also a tidal frequency, a little bit higher at this position. And then continuous decay at the 4 different positions in this moorings, at 4 different heights, actually, from the Coriolis parameter to the N here. These red lines are the local stability frequency values, which are related to the stratification. And the stratification is different, or the change of density with depth is different at different depth levels, so you have different values. But the spectrum or the internal waves range from F to N always, and then there's a spectral slope, which you have here as a black line, which is always like power law to -2. You have a peak here, maybe a cusp, and maybe also a little peak at the tidal frequency, but then a spectral shape like -2 at all the depths, actually. And if you go at other positions in the ocean, if you go to other positions in the ocean, you would also see this spectral slope. So it's a kind of universal spectral law for the internal gravity wave spectrum in the ocean. We call this the Garrett-Monk spectrum, or the GM spectrum. There's no real reference for that, or there are references for this, but there are a couple, and you never know which one. But this notion, Garrett-Monk spectrum, is a very standing thing in oceanography. So you can talk about the GM spectrum.
So it seems like we don't even have one clear decay, right? It's very little that between that forcing and the F and N. Can we clearly define an inertial range in that frequency band?
Yeah, well, there's a decay, right? It's not strictly -2, of course. There are differences. And if you go to different positions, then it's and if you estimate the slope, then it's -0.8 at 1.8 or 2.1. So it varies around -2, but it's always close to -2. It's just an empirical observation. It's nothing, there's no theory behind it yet. And also an M here, that's the vertical spectrum. You also see it maybe even closer here in the vertical spectrum, this shape -2, which is the black line here. And if you would have a spectrum of horizontal wave numbers, which is of course difficult to get from observations, you would also see hopefully the K of -2 spectrum. So this is what we observe in the ocean. There are internal waves everywhere in the ocean, and they fit like this. Of course, the total content of the energy, that's of course varying. You can move this line up and down. So the energy content is varying from place to place. There are sometimes more or less internal waves, but the shape appears to be like this. Okay, but you already saw this. There's a problem here. For normal plane waves, we have to assume constant environmental parameters like F, N, and everything. But here the N, the frequency is changing. The stratification is changing. So what to do with this situation is, of course, you have to invoke WKB theory. And I want to bring this a little bit closer to you. So we have a slowly changing environment in terms of this N, which is now function of Z, and also the mean flow, which we introduce here, also changes in horizontal position X and in vertical position X. The horizontal, or the mean flow, is supposed to be only horizontally, and it's in geostrophic balance, which we suppress here, but we have these relations. And then we have a plane wave ansatz like this for some variable psi, right? Some constant amplitude, horizontal wave number multiplied with X, and vertical wave number multiplied with Z, and frequency. You have your usual plane wave ansatz, which doesn't work in the situation with varying N and U. So what you do is you apply this wave-like ansatz, where you have an amplitude which is varying in space and time, and a theta, which is the phase here, which is also varying. There's a little parameter epsilon in front of all these dimensions, which is of course small. Epsilon is always a small parameter, right? Which makes these variations slow. And in analogy to the plane wave ansatz, we say that the derivative of theta with respect to time here is the omega or minus omegas and the frequency. And the same for the wave number vector and the vertical wave number, right? And they are also now varying. Of course, in the plane wave ansatz, K, M, and omegas, they are fixed values, but here we let them vary. And so in this small parameter epsilon, it's now indicating slowly varying amplitudes, frequencies, and wave numbers. But by this factor 1 over epsilon here in front of this argument of the exponential, we make sure that the phase in terms of k, m, and omega are still fast varying. So we have two scales, right? We have one fast scale or short scale, which is the wavelength or the period, and the long scale or slow scale, which is the variation of your wave frequency and the other parameters. And now the assumption is that the same is true, slow variation, for your velocity and the stratification. Also varies like this, right? So that's the assumption. That's the WKB assumption, that everything is slowly changing with a slowly changing environment. And then what you do is you use your ansatz, and usually you have a wave equation for the governing equations. You might have to be manipulating them into one equation that you call the wave equation, where you want to do a wave ansatz. You do this wave ansatz, and because you have introduced this small parameter, you have now orders or powers in epsilon. The zero order would be just terms without any epsilon in front. And you're supposed to sort them, the equations, into orders or powers in this epsilon, and they should be valid then in each of these powers or orders of the epsilon. And of course, the most interesting one is the zero order, where there's no epsilon. And you can see here from this, if you take a derivative, in your wave equations, you always have derivatives, right? If you take derivative, you have to do, maybe with respect to time, you have to do this product rule. There's one which gives you an epsilon from here, if you consider variation of psi hat. But if you take variation of theta, then you cancel your epsilon from the differentiation. And that gives you then zero order terms. But that also gives you the frequency or the wave number, very similar to the plane wave ansatz, right? And there you maybe can see that the zero order gives you the same as the plane wave ansatz, the same dispersion relation which we see here for gravity waves in this case, but it also works for other cases like Rossby waves, of course. And but the difference to the plane wave case is that you have not only dependencies of your frequencies on wave number, but now also on space, right? But slowly varying. And here the n is also slowly varying, and the u is slowly varying, and the k is slowly varying, and the omega. So everything is slowly varying here. And the other thing which you get is, of course, two frequencies. You have the intrinsic frequency, omega, which is the familiar or unfamiliar internal wave dispersion relation, which looks a bit complicated, and it's actually a complicated expression. It makes actually this capital omega to lie in between f and n, which we saw on the first slide. The dispersion relation has always been between f and n. And but now we also have the small omega, which is the frequency of encounter. So, and you have the Doppler shift by the mean flow, u dot k. Frequency of encounter would be the frequency which you measure. If you stay at a point with a mooring, then you would measure the small omega. But more familiar to you is the intrinsic frequency where you don't have Doppler shift. And that's the point. And the point is actually that you can change your intrinsic frequency by changing the Doppler shift by different Doppler shifts at different depths. That will become important later. And you can explain this with ray tracing, maybe. Who knows about ray tracing? A few. Who does not know about ray tracing? Who has no idea what ray tracing is? So few. So let me explain this to you a little bit. It's very related to this ansatz with slowly varying amplitudes and wave numbers and so on. And to make this point, it's convenient here to set this epsilon to 1. We don't need to talk about different scales here at this point. And also, we want to neglect the vertical, which is completely ridiculous for internal gravity waves. But for the sake of the argument here, it's easier. Otherwise, I have to add always m and z here in these relations. So I do this. And then we apply WKB ansatz, and then we have these dispersion relations, not only for gravity waves, but for all kinds of waves. Where you have a dispersion relation as a function of wave number, but also as a function of the local position and time. And there's the k also has a varying, has a dependency on the position and time, and the u. And still we have the frequency as a function of this derivative of the phase and this wave number also. And if you ask now for the change of omega, the capital or the small omega, I'm taking the small omega here, with respect to time, you have two time dependencies, right? One where the u, or here in the omega, the n, the stability frequency might depend on time. That would be an explicit time dependency. And the second one where the k also depends on time, right? So the wave numbers might depend on time. So you have to do two derivatives here. One with respect to this k time variation. You get by chain rule, you get this expression here. And then where you take k constant and only ask for this explicit time dependencies of u and n in this relation, right? And you might have noticed that this d omega by dk is nothing else than the group velocity, which I name here x dot. X means position and x dot means change in position. And you all know maybe that group velocity is related to energy propagation of the wave. And we will make this clear in a moment. So we replace this d omega by dk with the x, and we also bring it on the other side. And then the d omega by dt can be replaced with this relation here, with minus gradient omega. If you look at the definitions of wave number, if you take a d by dt here and a gradient here, you can see if you switch the derivative, you get the same thing, right? So you can make this relation, then you can replace this d by dt, and you get a relation like this, which looks like on the left-hand side, like a material derivative of omega following not fluid partial velocities, but x dot velocities. And x dot is then the position of your ray, right? Or x is the position of the ray. X dot is the velocity of the position of the ray, and this thing here is the material derivative. Then you can also do the same for lateral gradients of omega. There's nothing else here, just expansion. And you replace the d omega by dk with x dot again. You can also replace on the right-hand side here, you can equate gradient omega with minus dt of k. And you can come up with this relation with the minus sign here. That's the difference. But that's the same meaning, right? The material derivative of k, and the material derivative involves the velocity x dot instead of the partial velocity. So you say your x, that's not partial position, but ray position, right? And everything is analogous to the material derivative. And then you make this notation here. A dot means material derivative of your variable alpha, and then you have simple relations, right? X dot is d omega by dk, k dot, that's now, or x is the position of the ray, x dot gives you the velocity of the position of the ray, so you can follow the ray, and along the path of the ray, you have a change in the wave number vector, which is of course the refraction effect of a changing environment. And you can relate it to this minus gradient omega, which is the explicit dependency of omega on x by u, or u on x, or n on x. And what we have is omega dot is then related to changes in time of u and n, which we may allow for. Okay, so these are the ray equations, and you can use them to follow a ray. You can just calculate your ray and do some ray tracing with that, right? With just Lagrangian trajectories in a slowly changing environment. In our case, we also have z and m, and then you of course add the vertical group velocity, z dot, and you also go through the gradient m and so on to get this relation, and you add this also to the material derivative, so nothing else. So this is one complication which we have in 3D. There's a simplification which we can make. There's no time dependency in u or n, which we had in this previous slide. You say that's constant in time. To make it simple, then this omega dot is 0. So then in summary, we have these sets of relations and the dispersion relation for our waves in a slowly changing environment. And this dispersion relation was gained from the zero order in this expansion parameter epsilon from the wave equation, if you remember. Of course, you can also use first order. That gives you actually an energy equation. But that's a tedious task, and for these wave equations for gravity waves, then there's a shortcut. Shortcut is you take this paper of Ramanujan and Garrett, where I think this concept was showing up first. You see that this wave action is conserved for gravity waves. This is what you say, like Ramanujan and Garrett. And wave action is defined as energy over the intrinsic frequency omega. And that you take and you say, okay, or you note that A is not it's not really conserved like that A dot is 0 following a ray, but it's an action. That means that the integral over A is total action, and A is action density per space. So it's very similar to mass density. The mass of a fluid parcel is conserved, right? It's always the same. But the density of fluid in the fluid is of course changing because density is mass density. And for we have the continuity or mass conservation equation for mass, right? And fluid parcels where U is the fluid velocity, fluid parcel velocity. And this is the relation here. And d by dt, that's again the material derivative involving parcel velocity. We can call this rho dot if you want. And it's not 0, but if the parcels come closer together or spread away from each other, the density, the local density is changing according to this rule. And the same is true for the action density. A is not action, but action density, so A dot is not 0, but if the rays come closer together, then action is concentrated or they just dilute, the action is diluted. Yeah. It's a good question. Here it just stops from heaven, right? Or from Brotherton and Garrett's. Brotherton is in heaven, Garrett not yet. But anyway, but what you have to do, you have to prove this from the wave equation, right? You use your ansatz in the wave equation, and then you sort in order. 0 order gives you this local dispersion relation. That's always simple. But first order, you have to collect all first order terms, and then you have to manipulate them. And then after days of work, you end up with this relation. I will sketch you something similar for Rossby waves, but for gravity waves, I was too lazy to do. But probably Brotherton and Garrick did it. But it turns out that's always true. But it's not always wave action. For Rossby waves, actually wave entropy. So sometimes you have different relations, but there's always something which is conserved in this manner. Functional form, what do you mean by functional form? Just dependency.
Go back to what you first introduced. Yeah. So when you first introduced WK the ansatz, with psi is equal to psi hat of x y and z somewhere some t time and exponential. So this psi hat as a function of epsilon x, epsilon the rest of t. The functional form of the function would dictate the first order.
You mean if you would put in an epsilon square here, then you would get...
No, is that just a multiplicative like psi hat times the function psi hat?
Yeah, this is just a role model for U, V, B, the psi, as I didn't say, right? You have usually what you do is you have your equations of motions, and then you take divergence, vorticity equation, combine them, crunch them, and then you have a wave equation for W, for internal gravity waves. That's the usual standard way to get your plane wave solutions. And then you do the same, but have your wave equation for W and apply this ansatz then for W. Then you would have a W hat amplitude in W, sometimes this exponential wave function. Or you don't do this crunching and apply this wave ansatz for U, V, W, B, and P and everything, and apply this directly to the equations of motion, and then you crunch and try to come up with something. That's usually the way to get your dispersion relation and all this stuff. And okay, these are the ray equations, and here we have wave action. And you can imagine that doing this for the first order is then a task which takes some time, and you don't want to see this, right? So we take this shortcut here, and then we have this either this is then partial form of your continuity equation with rho dot. But there's also this flux form of continuity equation, right? And the same is true then for the A. There's also flux form for A, which you can motivate with fluxes across the control volume and so on, which maybe you've seen this for the continuity equation with volume fluxes and so on. Anyway, this is the action conservation equation. If you put in the definition of action, then you have a d, E over omega, and that calls here for product rule, right? One term where you take 1 over omega constant and take the time derivative with respect to of E, and then here there's the other part. With chain rule, you get a minus sign, but on the other side it's plus. And the same for the other terms, and also here the other terms. And what you get is then, well, if you multiply with omega, then you have here on the right-hand side the flux formulation for energy, and on the right-hand side, you see everything has an E over omega. The other omega cancels, and it looks like this, right? A times omega dot. If you add all these terms together, you have the rate of change of intrinsic frequency following your ray times A gives you energy change. And that means that the action is conserved, but the energy does not, right? Here there's a 0, here we have something on the right-hand side. And that's the energy transfer to the mean flow system, or the energy transfer from the mean flow to the wave. So that's like wave mean flow interaction in terms of energy. So that's the interesting term, because this is what we want to model and what we want to model in our parametrization, energy transfers in a consistent way.
So in the setup you're assuming the geostrophic flow doesn't have time dependence, right?
Yeah.
If you allow an epsilon t there, how would these equations change?
Yeah, that's of course an inconsistency. If you have, we say that the mean flow is fixed in time, and then now we are changing energy. We put in energy to the mean flow, then it has to accelerate.
But I'm asking more about the energy exchange problem. So you have this wave field is changing on a slower time scale, right? That's epsilon t. And if the mean flow also change on that time scale, would we get similar equations, or will there be more interaction terms?
That's difficult actually. If you put a t here, then everything gets difficult in terms of mean flow. You cannot really close the system anymore. That's a complication of the theory.
So in the ocean, what is your epsilon like? What are you thinking? Is it like order Rossby number, or is it something much smaller?
No, it's like Rossby number we took usually for epsilon.
Okay, so then the mean flow has to change on that 1 over Rossby time scale, right?
Yeah, but here in this ansatz, or in this construction, it's of course fixed. And it's fine for this ansatz, right? But that's usually done in theory rather than Garrett. Everybody does it. But if you construct a model, you're right. The model has an evolving U, and this is contradicting your ansatz. But at least we want to make sure that the energy transfer is the same from the parametrization, which leaves the parametrization and which enters the mean flow. That we want to match together. And that is consistent, energetically consistent. The theory is maybe inconsistent, but who cares about theory? We care about the model. No, this is of course just a joke. Okay, so we have these two relations, right? Energy, action conservation and energy equation, which is not conserved. And there's the omega dot, and we can calculate the omega dot from the definition of, or the dispersion relation here with intrinsic frequency and the extrinsic frequency. And if you dot this, capital omega, small dot of small omega was 0, then you have the dot of minus u times k. With product u, we get this. And of course, the u dot looks like this. There's no time dependency of u. So you have these two terms, times k. And the k dot you can replace with gradient of omega, and the gradient of omega only has a lateral gradient in u, because we said in capital omega there's the n, but that has no horizontal gradient, only vertical gradient. So we have only this u dot k as the gradient in omega. And it happens that this term and the first term, they can be combined into this expression here by tedious vector rules, vector algebra, which I don't show you. Because the second term, that's the more important one actually, with the vertical shear. And it's useless to talk about this so much, because that's not so interesting. And the second one, that's called wave drag actually, and it involves the vertical shear of the mean flow and the vertical group velocity. And I will talk about this a little bit, because this is an effect which we want to parameterize, both for gravity waves and Rossby waves. And this first term, that's related to horizontal gradients in U. That's also has been discussed. There are interesting effects. Sometimes that's related to called wave capture effects. But I won't talk about wave capture. But in the first term, that's the interesting one, and there's that dot, the vertical group velocity is involved. And I want to make one point here about the vertical group velocity. You have your dispersion relation written in this form, and you have to take the derivative with respect to m of this form. It's of course an involved operation. I show you here the result. It can be cast in this form, minus m times a function of this parameter, which is positive, right? Which shows you that there's a special relationship between z dot and m. M is the direction of the phase in the vertical, right? The phase propagates along the three-dimensional wave number vector, and its vertical component is m. So if m is positive, you have upward phase propagation. But then z dot is negative. That means you have downward energy propagation. And the other way around. If you have downward phase propagation, you have upward energy propagation. So kind of the phase propagation and the energy propagation, they are perpendicular to each other, actually. This is one aspect of this weird dispersion relation and the weird polarization of gravity waves. And we'll use this relation later, therefore I was mentioning this. But before we look at this gravity wave drag in more detail, we want to first check what is the fate of this energy, this A times omega dot. As we said, it's exchanging with mean flow, and we have to make sure that it's also ending up in the mean flow. So consider this. This would be a model equation, model momentum equation, where we put in a parametrization related to this energy stuff and wave ray tracing, and where we want to make sure that the energy ends up there, right? And capital U is the model velocity, and you have here these Reynolds stress terms, which are now not eddy stresses, which you usually have in your model equations, but the effects of the waves at U prime, E prime, and so are wave quantities, and you average them, and then they have no effect in your momentum equation or in your buoyancy equation. And of course, you have the same in the buoyancy equation, or in temperature and salinity equation, or in our tracer's equation, you also have these fluxes. But to avoid to list all the equations, we use here the residual momentum equation, where you can combine all the eddy effects or wave effects in a single momentum equation. And the trick is here to add this weird velocity, which is the wave or eddy-driven bolus velocity. Right, this is added here times f on the left-hand side and on the right-hand side. This is the definition of the bolus velocity. So you didn't do anything wrong here. And bolus velocity is a standing term in oceanography. Very important thing. Do you know? Who knows about the bolus velocity? Some do, but most of you don't. But there's the Gent-McWilliams parameterization for eddy effects in ocean models, right? Of climate ocean models. Who knows about the Gent-McWilliams parameterization? You know, okay. So this is parameterizing this thing, the bolus velocity. It's like an eddy-driven velocity, which shows up also in the tracer equation, in the B equation, right? As an advection velocity for the effect of eddies or waves. So it's not like a mixing effect, but like an advection effect. That's what the eddies or the waves do. In the ocean, they don't like to mix at this point. They will do later, but not here. And here you have a list of papers where this is explained in detail and why it's a good idea to do this. And the point is here that we only use this equation now for the wave effects, because we don't need to put this U prime, B prime term in the tracer equation. In the tracer equation, we have now the U plus VE as the velocity, which advects the tracer. And to first order, there's no difference in the U and this, what we call the residual momentum, U plus this eddy-driven velocity. So you can put, instead of the U here, in the first order terms in quasi-geostrophic theory, and which I don't want to talk about, except in the geostrophy terms, you can, it doesn't matter if you put U or U plus this eddy-driven velocity. So in your model, you take your original model, just rename your model variable like residual momentum, don't care about anything else, and just put this parameterization in, and you're fine. Yeah, but you also have the Reynolds stresses here, the usual ones, right? And they are now the ones which exchange energy with your waves. And so what you do is you form an energy equation for your momentum equation just by scalar multiplication with U each term. Then from the first, you get d by dt of u square half, right? That's your residual energy then, or your actual mean flow energy. And you do this with all the rest of the terms, and also with this and this. And we don't consider the others, only this exchange term, or which potentially gets an exchange term. Yeah, you take this thing, take scalar product with u, move the u inside the d by dz, then you have something which is the vertical part of a divergence, of a flux divergence, which in an energy equation is not considered so much because it integrates to zero if you integrate over the whole volume. The second term, which is the correction, that is an energy transfer. That is the energy transfer, right? And you can rewrite this maybe, the second part, using geostrophic balance for your mean flow like this. It's also a familiar relation, but you don't have to. And for the horizontal Reynolds stress, you do the same. You move this u inside the divergence and take it out and make a correction, and this would be the energy transfer due to this effect to the horizontal Reynolds stress. This is a bit involved in detail, but we don't need to do because that's the less important term. That was the more important term. Then you can call this exchange by vertical shear and by lateral shear. And vertical shear, as before, is the more important one. You have two components here, the vertical Reynolds stress and this eddy buoyancy flux. And now the trick for the parametrization, or to calculate this actually, is to use the polarization vector for gravity waves. For plane waves or for the WKB waves, it's the same. And I don't show you the derivation, but it's part of this tedious wave equation number crunching. You also get relations which relate u and w and b amplitudes to each other, like this here written in a vector times an amplitude, which is a complex number a. And it's, we don't go to details, but you can imagine that you can now calculate the correlation between u and w. Right? Turns out that the flux itself is the u times the complex conjugate of w. We're part of that, which you can calculate here, times the energy, because if you take the correlation, you get this a square is the energy. Right? So you can calculate each of these fluxes directly if you would know the energy, the amplitude of your wave fluctuations, which is given by the energy. And you can calculate any eddy correlation with this. Right? And that's the idea, to construct eddy parametrizations, because if you know, and to get some equation also for the energy, or to use the energy equation to predict the energy in the model, and then to use these relations to put your parametrizations for the eddy effects or the wave effects in the model. That's our concept. But before we talk about this, let's check if, when we calculate these fluxes, if they actually agree with what we have found before for the energy equation. So what you have to add is this thing here, this vector, times du by dz. And of course, there's an e, and also z dot times k times this du by z is common factor, and that's, of course, omega dot. The rest is happily converging here to the a, but with a minus sign. So you get the same term as before in the energy equation for the waves, but with an opposite sign. So that proves that the energy you take away from the mean flow enters the waves, the wave energy, or the other way around. Right? So you're fine, and that's what we call energetically consistent, that you don't produce artificial energy. Okay. And the same can be shown for the lateral part, but as I said, it's not so important. We want to focus on the gravity wave drag, right? And maybe I can go through this before the break. When is the break? 5 more minutes. Okay, the gravity wave drag. We make this a little bit more simple by saying n is constant, because then if you look at the z dot equation, the n dependency is here in the omega. And if n has no z dependency, dz dot by dz, the vertical group velocity has no vertical change. That comes handy in these relations, because then you can forget about these terms. And if we also say that the u has no lateral shear, then first the omega dot is only the second part. And we can also neglect all horizontal dependencies, also all horizontal group velocities. So then we get actually simpler relations. A dot is 0, and E dot is only this exchange with the mean flow, the energy exchange. Right? Just for the moment we do this. And then we consider signs of the different changes in time following the rays. So first we fix the k dot du dz with k in the direction that this holds here, the scalar product is positive, right? And then we start with upward phase propagation. The wave or ray wave package which propagates upward, m is positive. Then from the z dot relation, we have negative z dot because this f is always positive. Z dot is negative. Then you check this relation here, then because the scalar product is positive, z is negative with a minus sign, we have positive omega dot. And then you finally check your E dot equation. E is positive. So that means, or E dot is positive. That means that the energy, the waves gain energy from the mean flow. And then you start the other way around with negative m or downward phase propagation, and all the relations turn around, and you have loss of the waves, energy lost by the waves, right? But no, the point is in the ocean, an upward propagating wave will, or downward propagating wave with upward energy propagation will hit the surface, and the other way around it will hit the bottom. And then what happens is everything stays the same, except the m changes sign, right? The k stays the same, the frequency stays the same, the energy stays the same. So it will come back, right? And then it will, first it will gain some energy while propagating through the mean flow, and then it will lose energy. And then it will gain energy again, and then it will lose it. So there's no net exchange, no net energy exchange in the long run. This is one expression of the non-acceleration theorem by Andrews and McIntyre. You can formulate this for eddies or for waves, all the same. If there's nothing which breaks the symmetry, you have no net exchange between the wave and the eddies. There's no connection somehow. And so time is up. Dissipation is important and can break the symmetry. May I add here one point? The atmosphere is different. Many of you are from atmosphere, right? Hands up, who's atmosphere? Who's ocean? Ocean winds, that's good actually. But take one fast look in the atmosphere. There's no surface in the atmosphere, right? So upward propagating waves, they won't come back. They don't meet turning point or something special is happening. They must dissipate, right? And what they do is the air gets thinner and then the amplitude of the waves get larger because the energy stays the same, and then they break by convective instability. So that's what's happening in the atmosphere. That's not an issue here. And therefore, in the atmosphere, the gravity waves, they are more important, and they are discussed a lot, actually, because they are known to drive the meridian flow in the stratosphere, and in particular in the mesosphere, high up in the atmosphere, because all the upward propagating waves. In the ocean, that's different. We don't know so much about the effect of gravity waves. In the atmosphere, it's a big deal. And also the parametrization for gravity wave drag in atmosphere models. Maybe you have heard about this. Gravity wave drag parametrizations are often talked about. The ocean nobody talks about gravity wave parameterization, but I will. Okay. Then we make a break here. Or maybe there are some questions.
If you have any quick questions, we can have them now. Are there any questions? Yeah, there's questions online. Okay, then we'll break and come back.
Okay.
We will reconvene here at 11, and we continue to the second part of the lecture. There's actually a question online, Carsten. Is there a symmetry leads to conservation of action density? Maybe you can ask yourself, Pratik, online. You can just unmute yourself.
Hi, can you hear me?
Yes.
Yeah, so the question is that, is there a symmetry that leads to the conservation of action density that you showed? Or, maybe entropy conservation or some other conservation?
I'm not entirely sure if I understand the question, but the point is that by action conservation, we have the symmetry. But there's actually a point which I didn't mention actually is not conserved really. There's dissipation, right? Waves break. So there's not a zero on the right-hand side, but there is something. Nonlinear terms, dissipation, forcing, everything is affecting action then, and that breaks the symmetry actually. The dissipation, the breaking. So in principle, the symmetry is useless at the end. Does this answer your question?
Yeah, kind of, but okay. Like for example, my question was more on the lines of like when you have spatial symmetry that leads to conservation of the linear momentum.
Oh,
Something.
yeah. You mean a symmetry in the underlying equations?
Yes.
Equations of motions which give you this action conservation? No, I have no idea.
Yeah. Okay.
Yeah, that's a good question.
Thank you.
There's actually one more question online. Maybe you can also ask yourself, you can unmute and maybe to also turn on your camera. The next question. I can read out the question in the meantime. Do internal gravity waves on reaching the shore transitions into surface gravity waves? In that case, can we apply the same methods described here to surface gravity waves?
Can you put the question on the screen? It was too fast for me. Oh, you mean how to transfer the energy from gravity waves to surface gravity waves? And the second part, can you apply the same methods to surface gravity waves? Of course you can. You should do, actually. Actually, wave forecast model, they are based on all these ideas. And the radiative transfer equation, which I will talk about in a minute, it's all based on this stuff. So you should do this for surface gravity waves. And the interaction between internal gravity waves and surface waves is a bit tricky because there's not really a connection because they are usually, first they are in the mixed layer, right, surface gravity waves. And in the mixed layer, there's no N, so you don't have internal gravity waves there. So you must make a connection, and there's possibility of a resonant energy transfer between internal gravity waves and surface gravity waves, which we looked at, but this is complicated. And usually you don't talk about a connection between both. So, and also not at the shoreline. At the shoreline, you don't know what happens there. There's dissipation again, right? The waves break, and then who knows what happens. This is all nonlinear stuff, and we cannot deal with this so easily. I hope that answers the question. Are there more questions? No.
There is nothing more in the chat. Maybe we can resume then after the coffee break.
Okay.